Hello everyone, welcome back to another video. So today we are going to discuss solutions for biweekly contest 149. I was able to solve first three problems, then I tried fourth one for some time and I came to a conclusion where I cannot solve it. So I decided to make a video on first three problems. So I solved first three problems pretty fast, I would say. This third one could have been more faster because logic was after reading the question itself, I got the logic and solution for it, but I took some time in implementing it. Let's just start with first question. First question is pretty simple brute force implementation problem. So what we are given is a string consisting only digits, and we need to print a valid pair which is defined as two adjacent digits in S such that first digit is not equal to second, and each digit in pair appears in S exactly as many times as its numeric value. So we have to return first valid pair which is found while traversing left to right, and if no valid pair exists, we have to return empty string. First sample test case 2523533. This is the string. Now, if you check the element at second index and third index, that is 2 3, uh, both adjacent elements are not equal. One is 2, other is 3, and the frequency of 2 in the string is 2, frequency of 3 in the string is 3. So it satisfies all our conditions. So answer here is that substring of length 2, which is 2 3. Similarly, 2 2 1, here answer is 2 1. And in last case we cannot find any valid adjacent pair, so answer here is an empty string. There is no logic. I just basic implementation using a map. You can also write a brute force of n square complexity, but I used a map, so n log n works here. So first of all, I'm iterating over string C and storing its frequency. Now I'm iterating from left to right with starting from index 1. Then what I'm doing is I'm converting those characters which are in digit characters into integer d and d2. So d represents the current element and d2 represents its previous element. Now I'm just checking that condition that d must not be equal to d2, and mp of si, that is frequency of that character, must be equal to d, and frequency of its previous character must be equal to d2. If it is equal, then create a substring of length 2 with those adjacent characters and return it. And if we don't find any, we just return an empty string. So this was first question. Pretty simple implementation problem. Now let's move to second one. This is interesting question, I would say, but not that difficult. So what we are given here is a event time denoting a duration of an event, and basically it is a timeline which starts from 0 and ends at event time. So that's our timeline. And we are also given two integer arrays, start time and end time, each of length n, and these start and end time represents n non-overlapping meetings where ith meeting occurs during the time start time I and end time I. Now what we can do is we can reschedule at most k meetings by moving their start time while maintaining the same duration. And what we need to do is we need to maximize the longest continuous period of free time during the event. Now the relative order of all the meetings should stay the same. That means one meeting can be rescheduled before after its previous meeting and before its next meeting. It cannot go further. Now, so the meetings cannot be rescheduled out to the time outside of event. So after event time, this variable we cannot schedule the meeting. So let's just see a sample test case. So here event time is 5. So we create a timeline from 0 to 5. Now we k here is 1 and we are given start time end time of length 2. So there are two meetings. Now each block represents a meeting. So first block is represented by first block represents first meeting which starts at 1 ends at 2. Now second meeting starts at 3 and ends at 5. Now here maximum, here k is 1. That means we can at most reschedule a single meeting only. Now the optimal uh, meet configuration here is to move this one meeting which starts at 1 to uh, its next block, that is 1 to 2. Instead of 1 to 2 it should happen from 2 to 3. Let me show you. So this is our timeline. This is the first meeting and this is the second meeting. Now here maximum gap between any meetings is 1. So here it is 1, here it is 1, max is 1. After 5 there the event ends, so we cannot schedule any meeting after that. Now here optimal configuration after moving k meetings is to move this one to meeting here, then second meeting starts just after the first meeting ends. Now we have a gap of 2 units. So answer here is 2. Similarly, you can check this. There are 3 meetings and the optimal configuration here is to move the 2 to 4 meeting to 1 to 3 such that we have maximum gap of 6 unit times. So 0 to 3 there will be continuous meeting, 3 to 9 there will be free time, and 9 to 10 there would be uh, another meeting. So answer here is 6. Similarly for this case answer would be 0. You can check that out by drawing the block diagram. Now first let's try to break down the problem. Now let's say we are rescheduling at most k meetings. Now what is the optimal way of choosing those k meetings? It is kind of intuitive that we always choose k consecutive meetings. Only when we reschedule those k consecutive meetings, we have a higher chance of getting maximum gap. Maximum gap. Why is that? Let's say this is one meeting, this is one meeting, and this is another meeting. Now, if we according to our assumption, let's say this is an assumption. So what we can do is we can either reschedule these two meetings or we can reschedule these two meetings. Now when we reschedule any of those meetings, let's say this is an end. So this is 0 and this is our end time. So our meetings would look like this. Configuration would look something like this. So first two meetings, uh, rescheduling these two meetings will go towards its left, that is intuitively optimal. So we have this much gap. Now another way of doing it is either this reschedule these two meetings. So then what happens is this comes here and this is our gap. Now if we reschedule first and third, that is non-consecutive gaps, let's say, where can you put them? Optimally it is they are already at their position if we decide to go first and third meeting. So it would be something like this. The middle one can change. Let's assume that it is at the middle of exactly at the middle. Then we have G1 G2 gap. Now the main observation here is that the gap G would be equal to E minus sum of all its all the meetings duration. So E is our total event time and some, let's say xi, sum of all i's, xi, such that xi is the duration of in each meeting. So here G is that. Here also G is sum of xi. Both are equal. Here G1 plus G2 is equal to E minus sum of xi, because this gap plus this gap and all the sums meeting durations equal to E, and G1 plus G2 would be E minus sum of xi. So based on this we can say that G1 will always be less than equal to G. Similarly G2 will be less than equal to G. So it is always optimal to reschedule k consecutive meetings. So this was first observation. Now let's say I am at position I. This is ith meeting. This is I plus 1th meeting. This is I plus k minus 1 meeting, and we also did I plus k, I minus k. So we can reschedule k consecutive meetings. Now let's say we are rescheduling I to k minus 1 meetings. So either all of them can go to left. Now this meeting cannot be moved. Similarly this meeting also cannot be moved. So our gap, our limits, let's say this is the right wall, this is left wall, so this is our limit. Our limit is fixed. It would be equal to E of I plus, not E, start time of I plus k minus end time of I minus 1. Isn't that correct? So because this is I plus k is start and this is I plus k is end, and this would be start of I minus 1 and this would be end of I minus 1. So our limit is fixed. Now limit is fixed. What is the maximum gap which we can achieve? We can move all these meetings towards left. So what we can do is our limits, let's fix them. This is I minus 1 meeting, this is I plus k, this is our timeline, and all the meetings we move towards left. So I here, I plus 1, I plus 2 up to I plus k minus 1 are, we have moved towards left. Now this is our gap after rescheduling meetings from I to I plus k minus 1. So our gap would come out to be limit, which is the this which we found from this, minus sum of all i's, xi is duration, and here I is uh, let's call it j, and j is greater than equal to I, and j is less than equal to I plus k minus 1. So first, what are our options of choosing k consecutive elements? One, we choose 0 to k minus 1. Second, we choose 0 to k, 1 to k. Third, we choose 2 to k plus 1. We keep on doing this. So this type of solution, this is a pretty standard question of this concept, where we call this concept as sliding window. And so what this is, let's say 0 to k minus 1 is a window. Now when I'm moving to next index, that means when I need to choose next k consecutive elements, I will just move by 1 and move to 1 to k. So then when coming to next, it goes to 2 to k plus 1. So this is a window which slides towards right by one, exactly one step. Now there are also some in sliding window. This is a fixed step sliding window, means it will always move towards right with one gap. So left side and right side will always remain same. Size of that window will always remain same. Just starting and ending positions will move. So L and R would be consistent. There is also another variation where sliding window size is not fixed. But here sliding window size is fixed, and which is equal to k. Now to process k, what we need, sum of durations up till x0 to x k minus 1. And what is our limit? Limit would be the start of next element I plus 1, and it's uh, this end. So for processing 0 to k minus 1 window, end of our limit would be start of its next element s of k, and its limit start would be either 0 or e of I minus 1. Here it would be 0, but when we process a window 1 to k, end would be s of k plus 1, and start would be uh, e of 0. Now start and end presents our limit. Limit is end minus start. We also have sum. So we can find gap with limit minus sum and take its max for all k consecutive windows. Now how can we update this sum? At 0 index, sum would be 0 to k minus 1. Now when I am moving to, this is for first index, what I will do is, from previous sum I will subtract x of 0, and I will add x of k. So only two elements change. 1 to k minus 1 remains same, 0 gets removed, k gets added. So this is the concept of sliding window, main concept of sliding window. The change here is O of 1, or it can be O of log n. It cannot be greater or equal to O of n. So updates are linear or logarithmic. So this is the main solution. Let's just revise it once again. First find first objection, rescheduling case consecutive meetings is optimal. Meetings is optimal. Now what options we have? Either we have one, so we basically come to conclusion that we need to check for each k size window, 0 to k minus 1, 1 to k, 2 to k plus 1. Now when we are checking for 0 to k plus k minus 1, first we find limit, which is the start of next meeting minus end of previous meeting. This is our uh, limit. We cannot reschedule a meeting before it and after that because we have already used k meetings. We have limit. Now second is sum of duration of all the meetings from 0 to k minus 1. If we need to maintain these two elements, limit is just we can find from of 1 by just what we need is to check I plus 1. uh, this can be done in O of 1 by just basic indexing. The sum is where the sliding window concept comes in. So whenever we are moving to next, what we do is we its left limit we remove its duration contribution from our sum variable and add its newly added element. From k minus 1, when we move to next window, k would be added. When from k, when we move to next window, k plus 1 would be added. Similarly, on left side, when we move from 0 to 1, 0 is removed. Similarly, when we move from 1 to 2, 1 is removed. So this sliding window should be maintained. So let's just see the solution. So first of all, I have declared s dot size, and as s dot size, I have declared two variables. One is are to find answer to which stores maximum gap, and second is sum, which stores sum of all the duration meetings. Now for first sliding window, which is from 0 to k minus 1, I am pre-computing its sum. Now if k is less than n, that means our next meeting after the our window ends at k minus 1, then that means our next meeting would be kth meeting. Now if there exists a kth meeting, our total, that means our limit would be start of that k minus sum. Now we are not subtracting its end of its previous meeting because we are at index 0 and there is no previous meeting. So here uh, uh, the this variable end of previous meeting would be 0. So I'm just taking s of k minus sum and taking its max with answer variable. Similarly, if k is not less than n, that means there is a meeting which is that means there is no meeting after this. That means there is no kth meeting. Then our total would be the max time itself. So start of next meeting would be the maximum limit of our timeline itself. So that event time minus the sum. Then again I will take its maximum with my answer. Now here starts the sliding window. So I'm iterating by end of our sliding window. You can also do it with the start as a index of your sliding window, but it with I prefer iterating over ends of the sliding window. So second sliding window will end at k index, and the end can go up till n. Now, first of all, I will add duration of my next the newly added meeting and subtract its counterpart. That means the start of previous sliding windows meeting duration. It would be I minus k. So for 0 to k minus 1, uh, start was 0. So here I minus k, that means k minus k would be 0 and it would point to its start, uh, point to that meeting. Then I am subtracting its duration. Now I need to find total, that is our limit. Now if I plus n is less than equal to n, first of all our right side of uh, limit would be start of next meeting, so s of I plus 1. Else it would be just maximum limit of our timeline because there is no next meeting, and its end time of previous meeting of our starting window, it would be e of I minus k, and then take its max with total minus sum. So this was the second problem. I would say it was pretty easy. As you can see the submissions, it was definitely on easier side. Now moving to third problem. This was also easy. I'm not sure why this has very less submissions. Now this is same as second problem, only there are some conditional changes. First of all, we can only change one meeting, means we can only reschedule one meeting. Now, uh, so this is the first condition, and second condition is that we can reschedule this meeting to any point. Any point means we can reschedule it. The order of meeting can change, but there must be non overlapping. That condition is consistent. So this test case is better understanding of that. So 0 to 1 meeting can be rescheduled in 8 to 9. So in previous question, we can reschedule it in this up till 7 only. We cannot go beyond its next meeting, or we cannot go beyond its previous meeting either. So the order of meetings never change. But here we can only reschedule one meeting, but its order can change. Order of overall meetings can change. So from 0 to 1, we will schedule it to 8 to 9. Now what we have here is 0 to 7 as our gap. So here answer is 7. So this is a lot easier to explain, I would say, uh, in comparison to second problem. Its solution would also be a lot easier to explain. So let's say, first of all, what we need to do is we can reschedule at most one. So we can basically check for each meeting, if we rescheduled ith meeting, what would be the maximum gap. Now, if we reschedule this ith meeting, what are our possible options? One option is that keep it in its border. That means next to its previous meeting and uh, previous to its next meeting. So here answer would be, this is our limit variable which we defined previous question itself. Limit minus e of I minus s of I. So limit is our total limit, and e of I s of I is duration of our current meeting. So this is one option. Now second option is to reschedule this in such a way that it goes to any of the other gaps which there are possible. So we remove it from here and put it here. So here answer would be limit itself, because we have removed it and this whole gap is free now. Now to get this and put it here, what should be the condition? Only condition is that E of I minus S of I. This is our duration of this is the duration of our current meeting. So this should be less than equal to max of all the gaps, remaining gaps. Not this, not this. All the remaining gaps. So this is one possible gap. This might be one possible gap. This is a possible gap. This is a possible gap. So if any of the gap is greater than or equal to the duration of our current meeting, we can put it there. So our answer, one of the possible answer can be limit itself. If we cannot put it, then what possible answer we have is limit minus E of I minus S of I. Now here is a basic pre-computational technique, not even pre-computational technique, as basic I would say if you know how can we how to store those gaps, then then there we have a solution. So I solved it with multiset. So for first, let's start with the first index. So this is our 0 left limit, that is 0. So what are the gaps available to put this first meeting into these other gaps? So we have, let's call it G1 and let's call it G2. Now this can be easily calculated. Now if G1, let's say max of G1 G2 is greater than equal to E of 0 minus S of 0, then we can put our meeting in any of the gaps. So here answer would be limit itself, and limit is 0 to this. If it is not, means this condition fails, then our answer could be limit minus E of 0 minus S of 0. That is our limit minus the duration of that meeting. Now, how to maintain this? For first condition itself, let's say we we take only max of it. So I have mentioned max here, but we only take max. Now, when we are moving from 0th index to ith index, this gap G1 becomes invalid because this gap will be present in its limit, and that gap should not be considered as one of the possible available gaps. The only gaps possible is this G2. Now we cannot redo the max operation, right? Once max is done, we don't know its second max by just storing one variable. So we will have to use multiset. Why multiset? This gaps can be there can be multiple same value gaps. So only set would also not work. You can use set plus map or simply multiset. Both are same. Now this is so for first for checking 0th index, what we do is we add all the gaps. Now all what are possible gaps? S of 2 minus E of 1, S of 3 minus E of 2, and this goes to our event time minus e of n minus 1. I hope you understand this. So first gap would be start of second meeting and end of first meeting. Before all the gaps, they are invalid. So this is our start. So this would, we will keep all those differences in our multiset. Now, while moving to first index, which gap becomes invalid? This gaps become an invalid. S2 minus E1 becomes invalid. So what we do is we remove it from our multiset. Now, after this gap becomes invalid, there will be also a gap which becomes valid. I will show you at first index there will be no gap which will be valid, but let's move to second index. Now at this point S3 minus E2, not S3 minus E2. Here it would be just, yeah, here it can be S3 minus E2 becomes invalid. So we remove it from our multiset. But there is some gap which becomes valid. So what we are doing is we are checking for this. So G2 becomes invalid, G1 becomes invalid because they are in the limit of that meeting. But this gap, let's call it G0, G0, this becomes valid because this meeting can be put in here and limit would remain the max itself. So what is this? It is equal to E of 1 minus S of, sorry, S of 1 minus E of 0. So this would be added. Now when you go to third index, S of 4 minus E of 3 would be removed, but S of 2 minus E of 1 would be added. So as you can see, two there is a gap of two indices, 2 0 3 1, 4 2 3 1. So this type of information you need to take care of it. And multiset provides removal and addition insertion in login. So this multiset is perfect for solving this problem. So let's just move to its solution code. So first of all, let me remove this comment, debugging comments. So first of all, answer variable, which is our which is used to store maximum gap. Then we have declared a multiset. Now for first 0th index, we are putting all the possible gaps. Now gaps can be defined as a start of next meeting and end of current meeting, S of I plus 1 minus E of I. If there is a next meeting, if there is no next meeting, our ending time would be event time itself. Now again, total is to just find the limit first. So what I'm doing is, if there is a meeting after 0, that means if basically the size of our vector is not 1, that's what I'm checking, then total our limits ending point would be start of first meeting, else it would be its uh, the end of the timeline itself, that is event time. Now if there are gaps in our multiset and the maximum element of that gap is greater than equal to duration of current meeting, then we just take its max with total. That means the whole limit can be preserved. But if there is no such gap, our possible answer would be total minus E of 0 minus S of 0. That is total limit minus the duration of 0th meeting. So we have processed 0th element. Now I need to process all the elements from 1 to n. First of all, I am performing the removal operation. So I plus 1 less than n. So the gap, next gap. So for second, it would be s of 3 minus 2, e of 2. For first, it would be s of 2 minus e of 1. So if I plus 1 less than n, I will remove s of I plus 1 minus e of I. Else I will remove the event time minus e of I. I hope this is clear. Removal is clear. Now addition. Now addition would be s of I minus 1 minus e of I minus 2. We don't need to check if I minus 1 is greater than equal to 0 because I is starting from 1 itself. But we do need to check I minus 2. So I minus 2 is greater than equal to 2. I will subtract it from nw variable and I will add it to my multiset. Then I will find the limit, and after finding limit I will check if there is a gap which is greater than or equal to duration of current meeting. If there is, I will take answer with max of total. If there is not, I will take its max with total minus duration of current meeting. So this was third problem. Pretty easy to get the logic for this. Implementation, it might be difficult. Not difficult, but somewhat tricky to understand which gap to remove and which to add. Let's just check. "189 solves for fourth problem." That's interesting. So my rank is 228, but let's just check the ranks. I think my rank would come out around 210 after some days. I'm pretty sure, but 228 is not a bad rank considering I had 2500 rank in previous contest. So it was a pretty good contest for me. I hope it was good for you too. And that's it from my side. Thank you for watching.